Have you ever wondered if there's a hidden layer of reality, one where the rules as we know them fall apart? A place where particles teleport, spin behaves like it's on a digital dial, and objects exist in multiple states at once. Well, spoiler alert, you're already there. We call it the quantum world. And no, it's not some separate dimension buried deep inside atoms or accessed through wormholes. It's the very foundation of the universe. Every rock, every tree, every star you've ever seen, all of it is quantum. Always has been. So why doesn't it feel like it? Because quantum behavior tends to be subtle, hidden, overwhelmed by the big, noisy world we live in. But the deeper we dig, the more obvious it becomes. And now we're learning not just to see it, but to harness it. Let's start by unlearning what we thought we knew. In everyday life, things have a clear position. If you drop your phone, it doesn't disappear and reappear somewhere else, unless it's really lost. Objects move smoothly, can be pushed gently, and we can measure them precisely. These things feel like absolutes, right? Well, quantum physics says not so fast. Reality at the smallest scales doesn't play by those rules. It dances to a rhythm that's chunked, probabilistic, and honestly kind of weird. Take the idea of spin. If you spin a basketball slowly, you'd expect it to rotate just a bit at a time, right? But zoom in far enough, like really far, and spin doesn't come in gradual changes. It's all or nothing. Discrete. Quantum particles like electrons, for instance, don't spin smoothly. They're either up or down, like nature's tiniest coin flips. No in-betweens. Now here's where it gets fun. That spin? It's not even actual rotation. Electrons don't spin like tops. It's more like they carry a built-in twist, a fundamental, irreducible bit of angular momentum. It's baked into what they are. And it doesn't stop there. Quantum particles can be in two states at once. Not metaphorically, literally. This is called superposition. Imagine flipping a coin and having it be both heads and tails until you actually look at it. Sounds impossible, but this is standard behavior in the quantum realm. Then there's entanglement. This is when two particles, no matter how far apart, are so deeply linked that measuring one instantly tells you something about the other. Einstein called it spooky action at a distance, and scientists today just call it proof that quantum physics doesn't care about space the way we do. Oh, and about teleportation. Yeah, that's real too. Sort of. It's called quantum tunneling. A particle hits a barrier it shouldn't be able to cross, and yet it appears on the other side. No smashing through, no breaking the wall, just poof, it's there. These aren't just bizarre facts for science trivia night. They're the blueprint of a new kind of technology, one that's being built right now: quantum computers. Unlike the devices we use every day, which crunch data with bits, zeros and ones, quantum computers use qubits. These can be 0, 1, or both at the same time. It's like multiplying possibilities instead of adding them. With enough qubits entangled together, a quantum computer could simulate nature itself, crack impossible problems, and revolutionize industries from medicine to cryptography. But here's the catch: they're incredibly hard to build. Why? Because quantum states are delicate, tiny, fleeting, and unbelievably sensitive. Heat, light, vibration, any of it can destroy that fragile quantum dance in an instant. So to create and control qubits, we have to build devices colder than deep space. We're talking just a few millikelvins above absolute zero. At that temperature, certain metals become superconductors, meaning electricity can flow without resistance. But more importantly, all the electrons in those metals begin to act like a single quantum entity. That's when the magic happens. Using superconducting circuits, specifically ones called LC oscillators, we create systems where energy sloshes back and forth between two components, a capacitor and an inductor. It's like a bell ringing back and forth, but at the tiniest scale imaginable. And when these circuits are cold enough, that sloshing energy doesn't just move continuously. It becomes quantized, divided into steps, just like energy levels in an atom. These are the building blocks of a qubit. We then use precise microwave signals to control these energy levels. Think of it like playing the right note on a tuning fork. If you hit the right frequency, you can nudge the system from its ground state to an excited one, from a 0 to a 1, or put it in a mix of both. But there's a problem. If these energy levels were evenly spaced, we couldn't control them precisely. The solution? Add a non-linear element called a Josephson junction, a quantum device that allows us to fine-tune those levels and give each transition a unique signature. This is what makes control possible. The Josephson junction is fascinating in itself. It's essentially two superconducting materials separated by a thin insulating layer, so thin electrons can tunnel right through. That tunneling gives rise to quantum behavior we can harness and design around. This lets us treat an engineered piece of metal like an artificial atom, one that we can build, name, and control. And yes, it's as hard as it sounds. To keep the qubits isolated from noise, researchers house them in elaborate refrigeration systems called dilution refrigerators. These multi-stage cooling towers drop the temperature in steps, from room temperature down to just a few millikelvins. The entire setup is carefully shielded from electromagnetic interference. Special cables are coiled to prevent stray light. Magnetic shielding redirects field lines away from sensitive components. And at the heart of it all lies a tiny chip, barely visible to the naked eye, where all the quantum action happens. When it's time to read the qubit's state, we don't poke it directly. Instead, we use a technique called dispersive readout. The qubit slightly shifts the resonance frequency of a surrounding cavity. By watching how a microwave signal bounces off the cavity, we can infer whether the qubit is in a 0 or 1 state. It's like watching shadows to guess what's behind the curtain. So where are we now? Quantum computing is no longer science fiction, but it's not yet mainstream. We're still working through the kinks. Quantum noise, decoherence, hardware limitations, they're all real challenges. But progress is accelerating. At places like Lawrence Livermore National Laboratory and other research institutions around the world, scientists are refining designs, testing new materials, and building the tools we'll need for the next era of computation. What's amazing is that every experiment, every adjustment, every new insight brings us closer to technology that could transform the world. Imagine simulating new drugs before we even mix the chemicals, cracking unbreakable codes, solving problems we've spent decades calling impossible. It all starts by embracing the idea that the universe is weirder and more wonderful than we ever thought. And the best part, this strange world isn't hidden away. It's right here underneath everything. We've always lived in the quantum realm. We're just now learning how to use it.